Yes.
So, good afternoon, everyone. Again, I welcome you all to this 3 days international webinar on fundamental mathematics. I think you all have enjoyed the last session by Dr. Gautam Kolita. Today, we are again going to have a very interesting session by our very own Dr. Manjil Saikia. You already got the title and abstract. We have shared this abstract in the WhatsApp group yesterday. Again, I'm repeating this. The title of today's presentation is Basic of Permutations and Graph Theory using games. And basically, he is going to use the game in the Japanese ladder game. This is not about the game probably. We'll get all the idea during his session. But before starting his session, let me briefly introduce Dr. Manjil. Dr. Manjil is now he's pursuing postdoctoral fellowship. Research associate and at Cardiff University. He has completed his post graduation from Assam University and PhD from University of Vienna, Austria. He has published a number of research papers in very good international journals. He has also delivered lots of talks in various institutes like ISI. Then internationally, he also delivered lots of talks. Now we are very glad to have Manjil, Dr. Manjil, with us today. Now I welcome Manjil. Please come and present your today's session.
Thank you, Dimpal. But there is another issue now with my computer, so let me fix this. Sorry about this. Well, I was thinking of doing a whiteboard style presentation. I did not make any slides, and now my pen is not working. The computer pen.
Manjil, is it the issue with the Zoom app?
No, I think something is wrong with my pen because it was working till yesterday. Let me check once again. Yeah, it seems not to be working again. Okay, now it's working. Okay. Sorry about this.
Nothing.
Yeah, sorry. Yes. Let me share the screen. Okay, so I think you have to make me co-host because I made you host.
Okay.
Wait again. Yeah, can you allow me to share my screen?
I'm very new in Zoom app. That's why I'm checking for the. How can you allow Zoom?
So if you click on my name, I think. Let me check.
Yes. Okay. I'm getting it. Okay. Okay. Now yeah, I'm making a host. So
Yeah.
you
Okay.
please
Thank you.
start.
Okay.
Uh-uh.
It seems again it says that. Okay. Okay. Yes. Now it's working. Yeah. Sorry about this. So too many problems. Can you see the whiteboard in my screen now?
Yeah, we can see it.
Okay. 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 Let me start. So sorry about this, and thank you for patiently waiting for such a long time for me to start this. Today I'm going to speak about some basics of permutations and graph theory. And by basics, I mean really basic thing. So first of all, let me just mention that I am not an expert in the sort of things that I'm going to speak about. So these are just some things that I'm interested in. And yeah, and yeah, I use them from time to time in my work, but not really. I don't really work in permutations or in graph theory. So as a non-expert, I'm going to speak about all these things, and I'm fascinated by mathematical games. So I read a very nice paper recently, and I'm going to base this talk on this paper. So I'm going to give you the reference now. The paper is called Bugs, Braids, and Batching. And this is a very nice 17-page paper by Eloka, Dogarty, and Vasquez. And this appeared in the book. So this is a collection. So it appeared in a collection of very nice papers on recreational mathematics called the Mathematics of Various Entertaining Objects. Yeah, and this is volume 3, published by Princeton University Press. So this is a nice collection of some recreational mathematics papers, and one of these papers was titled Bugs, Braids, and Batching. And I'm going to base my talk on this paper. So if some of you have read this paper, then there is nothing new, and if not, then you can stick around and check. So the main purpose of this paper is to actually find a nice upper bound on the sorting number of circular permutations. So if you know something about sorting problems, then you would know that sorting problems are very important in mathematics and in theoretical computer science. Not only in mathematics and theoretical computer science, but also in other areas, it is very important that you know how to sort an array or how to sort permutations, especially. For instance, in molecular biology, it is quite important that you know how to sort permutations. So this paper, the aim of this paper was to find a upper bound for the number of ways of sorting a circular permutation using certain with certain conditions. And I'll now try to do this. Let me see how far I can go. But it should be a leisurely introduction and with not too much technical details. So the aim is to really show you that there are different ways of doing mathematics, and one of them is using something called games. So let's see. So the first point is that sorting problems are ubiquitous in mathematics, and it's important in mathematics, computer science, molecular biology, economics, and so on. Yeah, and games can provide a good tool to understand actually this type of understand this. Okay. So we start with a very simple game. And this game is called, as I mentioned already, Japanese ladders, right? So what we have is, first step is that draw 3 lines. Actually, we can draw n lines, but for the first case, we'll draw 3 lines called poles, labeling them. Okay. So, oops. So, first point is that this is called poles. And we draw some certain number of lines. Okay. So, and in the second case, second step, we label the bottom of each pole randomly. And then the objective of the game is to place something called rungs, or I mean ladders, if you will. Ladders across lines, okay, to create connections. So this is the objective, but it's not very clear what to do with this objective now. There are 3 different rules actually. So each number, so you remember that there are two sets of numbers. One set is above the lines and one set is below the line. So each number on top falls downward, and the rule how it falls is that if the number encounters a rung, it must cross it. Okay, so if there is a rung, it must cross it, and all the numbers on top must land in the place labeled by the same number on the bottom. So these are the rules, and maybe it is not very clear how to play this game, but let me give a small example, and then you'll understand. Okay, so let's start with the simplest example. So the simplest example would be, okay, I already mentioned 3 lines. Let me do, say, 1 line. So 1 line, there is only one way to label it, and label it below, and that is just 1 1. So there is nothing. So the game has no objective in this simple case. Let's go to 2 lines. So we have 2 lines, and then I label on top 1 and 2. And the second point was that we label the bottom of each pole randomly. So there are 2 poles now, 1 and 2, and there are only 2 ways to label below. So randomly, I can either label 2 1, or I can just label 1 2. And if there is 1 2, then you see that the objective is to place rungs across the ladder to create connections such that all the numbers on top must land. All the numbers on top must land in the place labeled by the same number on the bottom. So in this case, you see that the number on the top is already placed exactly with exactly the same number on the bottom. So the number on the top is the same as the number on the bottom. So there is no point in placing here ladders or anything because it is already matched. But in this case, it is not matched. So what we can do is we can do something like this. And what happens when we put a ladder here is that this number 1, it starts from here, and then it sees a ladder. So let me use a different color. So the 1, it starts from here, it sees a ladder, goes through the ladder, and then falls down. So the 1 falls to this one. Similarly, the 2, it starts here and then it sees the ladder, it goes to the ladder and then it falls down, and the 2 goes to the 2. So this is how you play the ladder game. So this is called the Japanese ladder game. Let's try for 3 ladders now, 3 lines now. So for 3 lines, let's say 1, 2, 3, and then I randomly label. So there are now many possibilities of labeling in the bottom, and I randomly label, say 2, 3, 1. Okay. So if it would have been a classroom, then I would have asked you how to do this. But since it is not very feasible here, let me do it myself. Okay. So first you see that the one, oops. So the 1 has to go to this one. Okay. And to go there, I need at least two rungs, because I have to go first from this point to somewhere in the second line, and then from the second line I have to go to the third line. So let me draw. Say I go here, and then I put it here, because the numbers are going downwards, so it's not going upwards. So it says each number on top falls downward. So the second ladder must be below the first ladder. So I put it here, and then let me check now. So the 1, it starts from here, sees the ladder, goes there, and then goes downwards, sees another ladder, and then finally goes to the 1 here. Okay, the 1 is matched now. Let's see for 2. Okay, so is the 2 matched? So we start with the 2, and then it sees this ladder, it goes across the ladder, and then it goes down, and the 2 is matched. So if 2 of them are matched, we actually don't need to check the last one, because the 3 would then be definitely matched. So the 3 starts here, sees this ladder, and then goes down. So you have also matched the 3. So this is a solution of this game for 3 lines. Okay. Let me just draw it again. So I have 2 ladders. So 1, 2, 3, and then 2, 3, 1. Okay. So this was quite easy for three lines. But in studying games of this type, in studying mathematical games, one of the major question is what is a strategy to win this game. Okay, so you win if you can place all the rungs so that the connections are made, and then you land on top of 1 lands on top of 1, 2 lands on top of 2, and so on until n lands on top of n. Okay, so that is the winning state of this game. And a natural question to ask in this type of situations with games and so on is that, is there a natural strategy so that you always win? So can you do it? So let's ask this question. So what can be a natural strategy? So for some of you, maybe you have already noticed where the permutations come, but I'll get to it, where you get to the permutations. So what can be a natural strategy? Maybe, okay, this is not yet proved or anything. So also to mention that in this talk, I'll be very loose, because my objective is not to really prove many theorems. It's just to show you how to think about different mathematical things in terms of games, or also to show you that there is something different that you can do with permutations and graph theory and so on. Okay. So a natural strategy might be that maybe you connect first say one of the numbers that is farthest from its final pole, and then repeat this technique. Okay, so this might be a natural strategy, that you connect first one of the numbers that is farthest from the pole, and then repeat this technique. Actually, we did that in this example. We did that actually because 1 was the farthest. So this was in the first line in the top, and in the bottom it was in the last line. So this was actually the farthest, and we tried to connect the 1. And once we connected the 1, the 2 and 3 automatically matched. But let's see. Let us move to a bigger example. So bigger, just 4 lines now, and let's say 1, 2, 3, 4, and a random labeling would be 2, 4, 1, 3. So this would be our running example throughout this. So this is the first state of the game, and let's use our strategy. So the strategy was that we try to connect the one which is farthest away. So here 1 is 3 away.
Manjil, sorry to interrupt you.
Yes.
But your video is not running.
Yeah, the video is not running because this is like a 2-in-1 laptop. So if I flip it, then the video becomes upside down. So I have closed it. Yeah, sorry about that. So I cannot really do it because it will look very odd if I do the video. Okay. So let's see. So the first.
No, Manjil, I was not asking about your video, but
yeah,
the slide is not working.
Oh, okay. Sorry. So really, it is not working.
Please write something. Let me check. No,
okay, I think it is okay. I see. So let me stop and then I do it again. Okay. So you can. So it's visible now, right?
Yeah, it's visible now.
Okay. So I think until this point it was visible the last time. Until this point.
Until the question.
Okay. What can be a natural strategy, right? Yeah. Okay. Let's see. So yeah. So I mentioned already that in studying games, one of the natural questions that you ask is that what is a strategy to win this game? And a strategy that we might think about is that maybe we connect the first one of the numbers that is farthest away from the final pole, and then repeat this technique. Okay. So and then this was the example that I picked up, and let's see. So let's see which is farthest away. So there are two candidates actually. You see the 2 is only 1 away from the 2, and the 3 here is away only 1 away from these 3. The 4 is 2 away, so the 4 is here, and then the 4 is here, and also the 1 is 2 away. So we can pick any of these 2 actually. So we can either pick 1 or we can pick 4. But since we are moving from left to right, so let me pick 1. Okay, and I will try to now connect the 1 to the 1. So if I put I have to put 2 letters at least, because I have to move 2 positions away. So I first connect a ladder here from 1 to the next, from the first pole to the next pole. And then since I'm going downward and I have to reach the 3rd pole, so I put a ladder here. Now the 1 starts from here, and then it sees this ladder, goes down, and then it sees this ladder and then goes down and reaches the 1. Okay. And we have also matched 2 actually. So the 2 starts from here and then sees this ladder and then it goes down. So the 2 is also matched, but the 3 is not matched because the 3 has to go, it has to go here to this 3, and the 4 has to go here. So it connects 1, it connects 2, and let me do a bet. Let me now try to connect 3 and 4. So I still have 1, 2, 3, 4, and then 2, 4, 1, 3, and I had this one and I had this one. So let me try to connect the 3 now. Yes. So suppose I draw this one and this one. Let's see if it works now. So it might not work, and maybe I need more. Let me check. So the 4, so 1 and 2. So 1 goes here, goes down. sorry, the 1 goes here, goes down, again it reaches here, goes down, again it reaches here and goes here. So the 1 is no longer matched, but the 4 is matched now. So the 4 starts from here and sees this letter, goes down, sees this letter and comes here again. The 2 is matched because the 2 sees only one letter and reaches the 2. Let's see for the 3. So the 3 goes here, sees this letter, goes down, sees this letter and again comes here. So the 1 and 3 is not matched, and except 1 and 3, all of them are matched. And you see that the 1 and 3, the position here is just adjacent to each other, 1 and 3. So if we just connect a letter here, and then the 1 was somewhere, the 1 ended up somewhere here, and then it sees this letter and goes. So the 1 ended up here previously, but now because there is a letter here, it will go down, see this letter, and then reach here. Similarly, for the 3, which was ending here in this point previously, will now land here. So this is one solution. Okay, and this was only possible because 1 and 3 was not matched and they were adjacent to each other. But this is not a very nice solution because you will see later on that there is a better way of doing this. But now let me just mention that this actually corresponds. So this solution corresponds to a permutation actually. And which permutation does it correspond to? So 1, 2, 3, 4. It corresponds to. So 1 goes to 3 here, and then 3 goes to 2, and 2 goes to 1, and 4, 2. So this corresponds to this permutation actually. And here we see the appearance of permutation. So if some of you know, then the rung should represent something like transpositions. But let me give a mathematical definition of permutations. So it's quite simple. So for me, permutation is actually a bijection from the set of first n natural numbers to itself. Okay, so permutation is a bijection from a set, so from a set S into itself. Okay, so this is a permutation for me. And for this talk, actually, we'll take that S is equal to some natural number, and we'll actually denote it by Sn. So for us, this is this would be the set S now. And there are several things that you can speak about. So for example, all permutations of a set of n elements into itself, all permutations of a set of n elements forms a symmetric group. Actually, forms a symmetric group. So forms a group, and that group is called a symmetric group with group operation composition. So if some of you know what is a group and so on, then this would be an easy exercise to do. Okay, so all permutations of a set n of n elements, it forms a symmetric group with group operation, that is composition. Now going back, so our permutation was, okay, how do I represent a permutation? So for me, representation of a permutation. So I already mentioned that for me the set is always 1 to n. So I have this set 1, 2, 3, 4 up to n, and any bijection from this set of n elements into itself would just result. The bijection would just result in taking 1 to one of these elements, and then 2 again to one of these elements, except the element for which takes 1 to that element. Okay, so let me be more clear. So let's assume that phi is the bijection Okay, so phi from S to S is a bisection, so Sn to Sn is a bisection, and 1 will go now to phi 1, 2 will go to phi 2, 3 will go to phi 3, and so on, and n will go to phi. And if I write using this notation, something like if I put two brackets and on top I write 1 to n, and below I write phi 1, phi 2 up to phi n, then this would be a representation of the permutation. Or in more short notation, I can just write phi 1, phi 2, phi 3 up to phi n. This would be another representation of the permutation, right? So let's see an example. So an example is the one that we already had. So we had 1, 2, 3, 4, and then we had 3, 1, 4, 2. So this I can write it in this way as well. So 3, 1, 4, 2, and so on. Okay. So this would be another way of writing it, right? So you can actually break the permutation into some shorter permutations. So this is a permutation of length n. Let's say length n. I mean, it's not probably the word that is used technically, but for our purposes, let us call it length n. And this would be the length 4. Okay. So you can actually, there is a result which says that you can actually break any length n permutation into a product of length 2 permutations, and these length 2 permutations are called transpositions, so which I had here. But I don't want to really prove that result or go into the details of it. But it might be useful to go back to our example. So I had this final state was this. Let me just draw this again and then see how you can read off the permutations actually. Read off the transpositions, this length 2 things. Okay, so I had 1, 2, 3, 4, and then I had bottom, I think 2, 4, 1, 3, and I had something like this. So I had 1 here, 2 here, and then 2 here, something like this. Okay, so if you read from say from the bottom up, so if you read from this direction, first you read that say this line, it connects 3 and 4, so you write 3, 4. Then this line, it connects 2, 3, so you write 2, 3. And then this line, it connects again 3, 4, you write 3, 4. This line, it connects 2, 3 again, so you write 2, 3. And then finally this one connects 1, 2. So you go from the bottom to the top, so you read along the rungs. So the bottom rung, this one connects 3 and 4. This connects 2, 3. This one connects then 3, 4, and so on. So if you write it in this way, this is actually a product now: 3, 4, 2, 3, 3, 4, 2, 3, and 1, 2. This will actually give you the permutation that you are working with. It will give you the permutation. So this is an easy way to check that any permutation of n elements is actually given in terms of transpositions. So this is a good time to write this. So let me just write it formally once. Let me, maybe I'll just mention as a bullet point. So let A be a multiset with elements from 1 to up to n. Then a Japanese letter, and any permutation really, is a representation of a permutation by the product I have I plus 1, and then this I belongs to A. So these are called transpositions for me. And what do I mean by multiset? So by multiset, you mean elements of the set can repeat. Okay. So for example, this is a set, 1 to 3 is a set. but 1 1 2 2 3 again 1, this is a multiset because the elements 1 and 2 are repeating. So this would be an example of a multiset. This is a multiset and this is a set. Okay, so this point that I mentioned, that the any Japanese ladder is a representation of a permutation by the product. This immediately actually gives us two things. So the first implication is that every instance of so let me just call a Japanese ladder game as JL. Every instance of JL has a corresponding permutation, because you can write any instance of JL as a product of permutation. So every instance will have a corresponding permutation. And in the other way, you can write actually that every permutation has a corresponding instance of JL, and this can be written as a product of adjacent transposition. Okay. So, however, this is not unique actually, because you can have the same permutation for 2 or 3 different games and 2 different instances, and so this is not really unique. But that is not so important for us. Okay. Going back now, was that the optimal solution? I already mentioned that this solution that we did, this solution was not really the optimal solution that we could do. And I already mentioned that there is a better solution. So let us now try to see if we can find a better solution. So for that, this product of transpositions would come in very useful. So we had something like this. This game, it corresponded to this product of adjacent transpositions. So this is an exercise really. I mean, it could be an homework. So prove that I plus 1, I plus 1, I plus 2, and I plus 1 is actually the same thing as I plus 1, I plus 2, then I plus 1, and again I plus 1, I plus 2. And the other would be, so this is 1 point, the other is that I plus 1 squared is actually identity. And this is actually for 1 less than I less than n minus 1. Okay. So these are two things that you can prove. Probably some of you have already done this in your courses, but using these two, we are now going to show that the above solution was not really optimal. There is a better solution. So we again do this, write down the solution. So we had 1 here, and then 2, and then something like this. Okay. So this actually you can transform it into using the first point. You can actually transform. So I'm going a bit fast because there is a lot of things that I want to show you. So if you go back to the recording and then pause it and check, then maybe it might be helpful for you to do it. Okay. So now I'm going to change this 2 3 3 4 2 3 2 3 4 2 3 3 4. Okay. So I had something like 2 3 3 4 2 3. Or is it the other way? So I think it is the other way. So 3 4 2 3 3 4. So this was 3 4 2 3 3 4. This part I'm going to change it to a 2 3 3 4 2 3, which is the same thing. So I have a 2 3 here. If I put a 3 4 in between, and if I have a 2 3, this is the same thing. Okay. So well, actually I need to have one in between. Okay. So this is a 2 3, this is a 3 4, and then this is a 2 3 again. So this is the same thing as the previous one. And now I have 2 instances of 2 3 2 3. You see here I have a 2 3, and here I have a 2 3. Now using the second point, that I plus 1 squared is equal to identity, I can just remove these 2 3, and then I get finally the solution. So 1 2 3 4 2 4 1 3. I just removed remove the 2 3 because this will be an identity, and now I have this. So let's check if this is a valid solution or not. So 1 starts here, sees this letter, goes down, sees this, and then goes down. Yes, 1 goes to 1. 2 was the easiest, so 2 sees this letter and then goes down. Now 3 starts here, sees this letter, goes down. And since 3 of them are already matched, you don't really have to check the other one. So 4 starts here, sees this letter, starts here, sees this letter, and then goes down. So all of these are matched. And this is a much more better solution than the previous one, because in this solution, you had to use 5 different rungs, but here you just use 3. And from going from 5 to 3, we just use these 2 very simple facts of permutations, of adjacent transpositions, to prove that the solution we have is, I mean, this has to be the optimal, because you cannot do it with 2 rungs. With 2 rungs, at least one of the numbers would not match with itself, because all of these are not matched. You see, 1 is not matched with 2, 2 is not matched with 2, 3 is not matched below with 3, and 4 is not matched below with 4. So all of them have to move somewhere, right? In this example, all of the numbers on the top has to move somewhere to reach the numbers on the bottom, and the only way to move is via these rungs that we have placed in between the poles. And if there is a rung missing in between 2 poles, then the numbers cannot move, and then there will be no solution. So the best that you could do is have at least 3 different rungs in this case, because the lowest possibility of rungs is 3. So this is an optimal solution, really, because you cannot do it with less than 3, and you could obviously do it with more than 3. We already did it with 5, but this is the best that you could do. Okay, so this is an example of an optimal solution, right? So before I go, so are there any questions, any simple questions that you have? Maybe Dimpal da?
Actually, Manjil, your this slide is again stopped.
Oh no, since when? So please stop me if this happens, okay?
Okay.
No. So, no, but I think I can see it because I'm connected with 2 different computers.
Yeah, now it's okay. Now it's okay. Yes.
Okay, so all of this was clear, right?
Yeah. It's visible now. Yes.
Okay.
Okay. Yeah, few questions are there actually. Few students have asked few questions. One question is from. Actually, I need the question. Lots of comments are there. Yes. One question is from Subrot. I guess that if we are given n number of lines, then there must be n minus 1 number of letters to solve the problem. I guess maybe.
Yes. So in this example, yes, but not always, because you could have something like, actually, let me just show something. So you have maybe 1 2 3 4, and then you could have this 1 2 and 4 3. Then only one letter would solve the solution. So it really depends on the bottom row. So if all of them are not matched, any I in the top row is matched with j in the beginning, where I is not equal to j, then yes, you need at least n minus 1.
Yeah, we have one more question, Manjil. Can you hear, Manjil? Yes.
Yeah, please.
So this question is from Vandana Yadav. Sir, if we just make a ladder between 1 2 2 3 and 3 4, it will be solved.
So, yeah, so this is what I showed actually here. That's right. Yeah. So I already mentioned while I was explaining that this solution was not the best solution, and then I showed that the best solution is here. So I did this actually to really give these 2 very simple properties, so that you can use these properties to solve. Yeah. So that's correct.
Yes. One more question from Vandana. So why would you make a ladder from 3 to 2 and 2 to 4? Sorry, 3 to 4.
3 to 4 and
3 to 2 and 3 to 4.
Well, it's not very clear because which letters he is referring to. So
okay.
I mean, here of course you have to make, because 3 has to go to the next pole, here, and then the 4 has to move until here. So you need 2 at least. But yeah, because of the way the talk is happening, so it is not very clear.
Yes.
Okay.
One obvious question is from Jiras actually. Is it necessary all the numbers distinct? So,
Yes, of course. Otherwise, the game has no
yes,
meaning. So yes, it is necessary because we are in the realm of permutations, and then you have a bijection from a set to itself. So the number has to be distinct. Otherwise, it is not a bijection. Okay. All right. So let me continue a bit. So it seems that I will not be able to do everything. So maybe
okay.
I'll just do a little bit more about permutations and then go to graph theory. Okay. So this actually presents a strategy. So the strategy actually this is actually a good strategy. Good strategy in the sense that if you use this strategy, then you will be guaranteed that you will have a solution. And the strategy is there: clean up the transpositions. So that is what we did actually. So in the previous example, we had some repeated transpositions which we cleaned up. In one case, I used this identity, and in the other case, I used that product of the same adjacent transposition is the identity. So this classic problem of sorting permutations actually give an optimal strategy. Okay, this is not a very new problem. This problem has been there for a long time, and I'll just present the strategy very briefly because it introduces a very important concept which is called inversion number of a permutation. Okay. So I'll just present the strategy briefly. I'll not really prove it, or let's see how it goes. So maybe I'll not prove it. Okay. So in the first case, we assume that say a1 up to an are the numbers at the bottom. Okay, are the numbers at the bottom. Then an inversion. This is important. An inversion is any occurrence of ai aj with I greater than j but ai less than aj. So this is an inversion, example of an inversion. And let k be the number of inversions. So this is the total number of inversions in a1 up to an. Then the claim is then k is the number of k is the minimum number. Actually, k is the minimum number of inversions that we must do, that we need to solve the game. So this is intimately tied up with this very important concept of inversion number. Inversion number in itself is a very widely studied statistic of permutation. So the strategy now is that from left to right, first find inversions and transpose the elements. So this is a strategy that we can use actually. So let me maybe just skip saying more about this. You can think about this strategy and see if it really works or not. So the strategy is to really find the inversions and then transpose the elements in that inversion. Okay, so that is how you would solve the Japanese ladder problem. Let me just go now to a different style of Japanese ladder, which would now be based on. So I'll add a little bit more rule into the game. Okay, so let us call this enhanced Japanese ladder now. Enhanced Japanese ladder or EJL. So how we do is that we change, the first change would be that change the rungs into arrows. Okay, into arrows. And if if a number crosses a rung in opposite direction of the arrow, then the number then the number changes sign. And if a number crosses a rung in same direction of the arrow, then it remains unchanged. It remains unchanged. So what do I mean by this? Let me just give an example. So I do the very simple example. Okay, so this is a solution. Okay, for the normal Japanese letter. So 1 2, I'm matching it with 2 1. Now if I place an arrow, so let's do this. So if I place an arrow here, then you see that the one, it starts from here, it sees this arrow, goes to this direction and then lands here. So it is moving in the same direction as the arrow. So the number that is in the bottom is just 1. But the 2 starts here and then it reaches this line and it moves in the opposite direction to the arrow and goes down. So the 2 will change the sign and become a -2. Okay. So the game, instead of just having these rungs, we now have arrows where the arrow has a direction head in one direction, and then if the number moves along that direction, then the number is not changed. But if it moves in the opposite direction, then we put a minus sign. That is just the change that we have done. Now this immediately you can see that this game is more complex than the other one, because we now have to keep track of arrows and so on. Okay. So let's go back to the old example actually, and so the idea is again that what can be the optimum strategy for this game. Can the strategy from the last game be used in this game as well? Let's see if it works. Okay, so we had this 1 2 3 4, and let me use now these numbers. So we had 2 4 1 3 in the previous case, but now I'm putting a minus sign. So -2 4 -1 -3. Let's see if we can have a solution for this or not. Okay, so let me first write down the solution that I had in the previous example. So this was the solution for the previous game, right? So this was the solution that we found with only 3 letters. Now is it possible to put arrows? Well, let's see. So I need the 1 to change the sign, right? Because the 1 in the bottom has a minus sign. So there are two arrows that we can put, one in between the first and the second line, and the second in between the second and the third line. Okay, sorry about this. So I need the arrow to change sign, otherwise the 1 will not become a -1. So let me put an arrow here and let me put an arrow in the opposite direction here. Now why I put the first arrow in the same direction was because the 2 also has to change sign, and the 2 has to become a -1. So the first arrow has to be in the opposite direction of the movement of the 2. So the first arrow goes from left to right and the second arrow goes from right to left. Now I have matched 1 and 2. Let's see how we can do 3. So the 3 example is the simplest, because the 3 has to move only 1 arrow and then it has to change to a -3. So the direction of the arrow has to be opposite to the direction of the movement. And I now have 3 which goes to -3. And does this work for 4? Let's see, the 4 moves in the direction of the arrow, so it does not change sign in the first arrow. Again, it goes down and again moves in the direction of the arrow, and it does not change sign. So the 4 goes to a 4. So we have actually a solution for this instance of the enhanced Japanese letter. But is this optimal? This example cannot be solved in less than 3 runs, that I have already explained why it cannot be solved in less than 3. So if I change slightly the signs, can you do this in this same manner? Is it possible to do it in the same manner? So I have 1 2 3 4, and now instead of -3, if I just have a 3, can you do it? So this is an exercise. Think about it. And Let me very quickly go now, move on, because there is not much time. So previously, in the previous example, we had permutations. So a Japanese letter corresponded to a permutation. And in this example, since we have signs, the enhanced Japanese letter will correspond to now something called signed permutation. And this is something that I'll not discuss because of the lack of time, but let me just give the definition of a signed permutation. A signed permutation is a map, say phi, which goes from 1 to up to n, and it goes to plus minus 1 up to plus minus n. Okay, such that if phi of I is equal to some k, then phi of j is not equal to plus minus k, where I is not equal to j. Okay, so that means each of the i's in the first set, in this set, correspond to a unique element in the next set. Okay, so but this is not a bijection because this set has more elements than the first set, so this is not a bijection anymore. Okay, so how many signed permutations can there be in this set? Oh, this I forgot to mention. So the number of permutations of an element set into itself is actually n factorial, and this is not very difficult to see. Yeah, maybe I'll not mention it. So number of permutations is actually number of permutations on 1 to up to n factorial, which is and the number of signed permutations, this n factorial is just n into n minus 1, n minus 2, and so on up to. And the number of signed permutation on this set is now n factorial times 2 to the n. Okay, so these are very simple counting problems that you could try to prove on your own, and I'll not really explain it. Okay, so one main point that you could that differs that is the difference between the enhanced Japanese letter and the Japanese letter game is that in the Japanese letter game, all permutations were realizable by the game. Okay, there were the game any game could be written as a permutation, and any permutation was possible to write in terms of the game. But in this case, in the signed permutation case, not all signed permutation are realizable by enhanced letters. Okay, for n equal to 1, it's not it's easy to see, but you could try with n equal to 2. So for n equal to 2, if you put n equal to 2 here in this formula, then you see that there will be 8 different signed permutations, and I'm saying that out of this 8, only 4 of them will correspond to enhanced letter game. So that is something that you could check on your own. Okay. So let me just mention how you could probably think of the right direction of the optimal strategy. So you could one fact that you can observe is that the product of the signs in the final state, okay, in the final state, that is in the bottom row of an enhanced Japanese letter game is -1 to the power k, where k is equal to the number of rungs in the game. And this is not very difficult to see. So here you see that there were three minus signs and there were 3 different rungs. So yeah, so that is why you have the product of the final state, you have it to be -1 to the power k, okay, where k is the number of rungs in the game. And you can easily see that the product here would be 1. The signs would be 1, -1 into 1 into -1 into 1. And I already said that the minimum number of you need at least 3 different rungs here. So this game is not solvable actually. That this would give a proof of that. But you could try, because this is a very easy example, n equal to just 4. So it might be possible to do it hand. Okay. So this is how you would think about an optimal strategy in this enhanced Japanese ladder game. So this type of enhanced Japanese ladder game is related with braid groups, which are important class of groups that one studies in algebraic combinatorics, in geometric combinatorics, and many different areas of mathematics actually. But I'm not going to really say about braid groups. So if you are interested, you can read. So these are connected with something called braid groups. But I'll skip over this part. Okay? And I'll go now to the third variation of the Japanese game, which would bring me to some graph theory. Okay, so let me end this part here, and then now go to the third and final part that I had, which would be now something to do with graph theory. So again, I want to change this setup, okay, of the Japanese ladder game. So earlier I had this series of lines in the plane. Now I want to play the game in a cylinder. So I have a series of lines. I draw it in a cylinder. So imagine that I have a cylinder. So I have a cylinder. Well, maybe this is a small cylinder. Let me draw a big cylinder. So imagine that I have a cylinder, and now in the cylinder I draw the lines. So I have these lines, and then there will be some lines in the back as well. Okay, so I have this 1, 2, 3, 4, and then this will be n minus 2, n minus 1 up to n. So I have these n lines in the cylinder. Okay, and I have the same rules of the game. On the top row of the lines, I put 1 up to n, and on the bottom, I randomly put 1 up to n. Okay, maybe this is like 2, 4, 9, 7, and then here maybe it's like 13, and then here is n, and here is n minus 5 or something like that. Okay? The objective is same. You have to put rungs in between these poles, and then you have to match the top row with the bottom row. But the only difference is that now you can also put a rung between the column marked n and the column marked 1. So it is also possible to put a rung between this pole which is marked n and which is marked 1. So that is the only difference. And you can think of playing this in a cylinder instead of a plane, like we did in the previous case. Okay. Now, since I'm talking about permutations, I talked about sign permutations. So many of you have probably now realized that this time I'm going to speak about circular permutations, because this is actually a circular permutation. So what is a circular permutation? Circular permutation can be written. So you have a circle, and then you just write the numbers from 1 to n in this circle in any random order you would like. Say 1, 3, 4, and 2. And this would be now a circular permutation. So 1 goes to 3, 3 goes to 4, 4 goes to 2, and then 2 goes to 1. And the notation that I would use is something like this: 1, 3, 4, 2. So this would be now a circular permutation. So this belongs to the set of circular permutations. Okay. And as a group of permutations, actually this set of circular permutations is isomorphic to the set of permutations. And the only difference is that the generating set of the permutations was the adjacent transposition 1, 2, 2, 3, 3, 4 up to n minus 1 n. But in this case, the set of the generating set is now 1, 2, 2, 3, 3, 4, n minus 1 n, and then n 1. So the generating set is now 1, 2, 2, 3, minus 1 n and 1. So this would be now the generating set of this circular permutation. So you would notice that this representation is not actually unique. You could write the same permutation like this. So you could start from 3, 3, 4, 2, 1, which would be the same permutation, same circular permutation, because you are moving in the circle. And again, this would be the same permutation. 2, 4, 2, 4, 2, 1, 3 would be the same permutation. And you would have one more, which would be now 2, 1, 3, 4. So you actually have 4 different representations of the same permutation. And you can prove that if you have n if you have an element circular permutation, then there are two n equivalent expressions of a single circular permutation of n objects. And so let me just write actually. Well, maybe I'll just skip. So you can also go in the reverse direction, right? So you can go in this direction as well. So 1, 2, 4, 3. I went in this direction for these examples, but if you go in the reverse direction, it is still the same circular permutation. And you will get 4 more. So there will be 8 different representations of the same circular permutation on 4 elements. And in general, I'm saying that there are 2 n equivalent expressions of a single circular permutation of n elements, n objects. Okay, and these are the 2 n permutations of the dihedral group. If you know what the dihedral group means, then this would be just the permutations of the dihedral. So what this means in our case, for our example, is that this means that we have to consider equivalence classes. Okay, in this circular ladder game, we don't have to consider all of the objects, but if we consider equivalence classes, then it is okay, right? And sorting circular permutations and sorting the circular ladder game is now equivalent, because earlier it was equivalent of sorting a normal permutation, and sorting the ladder game was equivalent. And this time you have seen that the circular ladder game is now same as the circular permutation. So our objective is actually to sort the circular permutations in some sense. So there will be now some notations that I'm going to use. Let's say, because it is so let Ln be the set of all circular permutations on n objects. And now Ln is, I already mentioned that it is generated by let's call this set L, which is now given by, so this will be a shorthand expression that I'll use, and I'll write what this expression means. So it is given by this sigma 1 up to sigma n, where sigma I is now I plus 1, I plus 1 for I less than equal to n minus 1, and sigma n is now n1. So this is the notation. So this I already mentioned. Actually, it is already in the line above that this is the generating set. Okay. And let us define now a relation on this, so that we go to the equivalence classes, because I am not interested in all the circular permutations. I'm interested in only the equivalence classes, and the relation is just now, well, it is very easy to define. So these are just permutations. You just permute the circular permutations using the permutations of the dihedral group on 2 elements. So if sigma and tau belongs to Ln, then sigma is related to tau if and only if say sigma can be written as a product of two things. So sigma can be written as a gamma times tau, where gamma is now an element of the dihedral group on 2 n elements. Okay, so this is just now either rotation or flipping. So you can think of this as either rotating the circle or just flipping the circle on its diameter, right? So these two would be the elements of the dihedral group that you are interested in. Okay, so once you have a relation, you can go to the equivalence classes. So let us now define the quotient of this relation. So let L prime n is now Ln mod this relation. Then how many elements are there in Ln? So, clearly the number of elements in L prime n is now the number of elements in Ln divided by 2n, because there are 2n equivalence classes, and the number of elements in L prime is now n factorial, which is now given by n minus 1 2 for n greater than equal to 3. But I'm saying that L prime n is equal to 1 when n is equal to 1 and 2. So you just check this. It's not very difficult to check. This is quite an easy example actually. So circular permutations are much more difficult to study than normal permutations. And already, you know, the problem that we solved for the normal permutation, that given n poles, what is the minimum number of rungs that is required in the circular ladder game? This is not immediately clear in this case. So you have n poles, and you want to find out the minimum number of rungs that is required in the circular ladder game. So this is not clear. Also, the algorithm for finding the most efficient solution in a circular ladder game is still open. There is no efficient algorithm that you could find. But we can answer an easier question, which is that is there an upper bound on the minimum number of adjacent transpositions that is required to factor any arbitrary circular permutation? So remember that we used adjacent transpositions when we were studying the normal Japanese ladder game. When we were studying normal permutations, we used adjacent transposition, and we wrote the game in terms of product of adjacent permutations, adjacent transpositions. Can we do the same thing for the circular Japanese ladder game? So the question is, find an upper bound on the minimum number of adjacent transpositions. L is now the so this script L, which is now the generating set, required to factor an arbitrary circular permutation in L prime. So in the conjugacy classes, I'm not interested in the whole set, but in the conjugacy classes. Well, actually, there is a upper bound, which is now, which is a very simple upper bound that you can actually check. But I'm not going to really mention the details about this. So to study this problem, we would adopt a graph theoretic approach. Now I'm going into the graph theory part. So if some of you know what is a graph, then the preceding discussion for say 5 minutes would not be interesting for you. What we do is we study something called graph. So a graph for me is, actually a tuple of sets for me. So a graph G is equal to two different sets V and E, where V is the set of vertices and E is the set of edges. Okay. And the geometric way of representing is that the set V, suppose the set V has elements V1 up to Vn. For let's say n equal to 4, I put dots in place of the elements. So this dot would represent V1, V2, V3, and V4 in any way. Okay, and then E would be now a collection of edges. So let's say E has E1 up to EM, and these edges would be lines between any V1, any VI, and VJ. So this would be actually lines in between VI and VJ. With some condition, okay, with some condition. So if I draw a few lines here, let's say I draw to V1 to V3 and then V4 to V1 and then V1 to V2. This would be a graph. So here G is equal to VE, where V is equal to now V1, V2, V3, V4, and E would be now just V1, V3, V1, V4, and V1, V2. So these are the edges. So V1, V2, V1, V4, and V1, V3. So this is an example of a graph. It's a pictorial representation of two different sets, where one set is a set of vertices which are represented by dots, and the other set is a set of edges which are represented by lines between the dots, where you draw a line according to certain conditions that you place on that set. Okay. So we need some more notation actually. So there are several things that we can do. Once you have this graph, then you can define the degree of the vertex. So the set V is called the set of vertices and E is called the set of edges. So a degree of a vertex is now equal to the number of edges adjacent to that vertex. So this is the degree. So for example, here V1 had 3 edges connecting it, right? V1 to V4, V1 to V3, and V1 to V2. Then degree of V1 is now 3 because there are 3 edges. Similarly, degree of V3 is 1 because only one edge is connecting V3 to any other vertex. And degree of V4 is 1 because it has only one edge. Degree of V2 is 1 because it has only one edge. So this is the degree of a vertex. Okay. Now in a graph, well, let's say a graph is called n-regular if all vertices have degree n. So the above graph is not any n-regular graph because the degree of the vertex were different for each of these. Each of the vertices had different degrees actually. Well, not different. So some of them had the same degree, but it was different from the degree of V1. But let us consider this graph. So this is now a triangle, and this graph has degree 2. Let's say V1, V2, V3. So V1 has two edges going adjacent to it. V2 has 2 edges adjacent to it, and V3 has 2 edges adjacent to it. So the degree of each vertex in this graph is 2. So this graph is an example of a 2 regular graph, right? So this is the definition of an n regular graph. You need some more things actually to transform. So the objective that I have in mind is that I want to study this question, and I want to study this question using some graph theoretic technique. Okay. And so to study this question in terms of graph theoretic technique, I need to transform this question into a question about graphs. So that is the objective that I have in mind for doing all this. Okay. So I need a few more definitions. See, so let d v1 v2 be the minimum path distance. Okay. I'll explain what is a path distance. Minimum path distance between V1 and V2. So what do I mean by path? So you can have a graph. So let me draw a very yeah. So okay. So this is a graph. So this graph has six vertices. Okay, 6 vertices. So V1 and V2. Let's consider that this is V1 and this is V2. Okay. So now by a path I mean well, the normal English definition of the path applies actually. So you want to go from V1 to V2, and in the path you want to use different edges. Okay, so one path would be that you go from here to here to here. This would be one path. Another path would be that you go from here to here, you go to here, then you go here, and then you go here. So this would be a different path. And d of v1 v2 means the minimum path distance between v1 and v2. Now what is the minimum? The minimum is actually distance 2. So the minimum in this case was that v1 goes to this vertex and then it goes to this v2. So the minimum distance is 2 in this case. But you understand what do I mean by path. Okay, all right. So dv1 v2 is the minimum distance. Then by eccentricity, well, I'll change the color. So by eccentricity of a vertex v, I denote by say e of v, which is now the largest distance between v and any other vertex. Okay. So what is the largest distance? So here v1 is distance 2 from v2, and v1 is distance 1 from this vertex, and similarly from this vertex it has distance 2, and to this vertex also it has distance 2. So the eccentricity of V would in this case be 2, because the largest distance in between V1 and any other vertex is 2. All right. Or you could write in terms of the distance function that we defined was that this is now the maximum of B of V comma Vi, where Vi is now a vertex. So this is the maximum of the distance that you have. You can define radius of a graph. So radius of a graph, which we denote by R, is equal to now minimum eccentricity of any vertex. And diameter of a graph, it's not 2 times the radius in this case, but it is now D is equal to maximum eccentricity of the graph. So this would be, these are the definitions that we need for studying this problem. Okay, so how do we adapt this graph theoretic method? So I want to transform my graph. So remember, we are considering the equivalence classes of the circular permutations to study the circular Japanese letter game, right? So what we want to do is now we'll make a graph out of that. Okay, so for the graph I need 2 sets. One is the set of vertices V, which I'll take to be the equivalence classes L prime N, and say E edges would be V1, V2 are adjacent. So 2 vertices are adjacent if V1 can be formed from V2 using an element in L. L was now the generating set, so which was sigma 1 up to sigma n. Okay, so V1 and V2 are adjacent if V1 can be formed from any element using an element of this generating set. Okay, so if you can go from V2 to V1 using an element of the generating set, then V1 and V2 will have an edge between them. Okay. So what this means is that V1 and V2 are adjacent if and only if V1 can be formed from V2 by making an adjacent adjacent transposition, right? So cyclically adjacent transposition, because this L set was the cyclically adjacent permutation transposition set, which was generating the circular permutation. So this means just that V1 and V2 are adjacent if and only if V1 can be formed from V2 by making an adjacent transposition, a cyclically adjacent transposition. Okay, so you can prove actually some results of this graph. So now the graph G would be V comma E, where V is now L prime N and E is this set. Okay, and let's denote this because there is an N involved. So let's call this Gn. Right? So there are some results that you can prove actually immediately. So you can prove that every vertex in the graph has the same eccentricity. Okay, the same eccentricity. So if it has the same eccentricity, because the radius was the minimum of the eccentricities and diameter was the maximum of the eccentricities, so an easy corollary is that so radius is equal to the diameter, because the eccentricity is the same for every vertex, right? Now let us come back to the question that we had. Okay, the question was here. I had written the question that we want to find an upper bound on the minimum number of adjacent transpositions that is required to factor an arbitrary circular permutation in the equivalence classes that we have. Now this can be written in terms of a graph theoretic question. So the question becomes, determine the diameter of the graph Gn actually. So why is this the case? You see that the diameter was the maximum eccentricity, and the eccentricity was the largest distance between any vertex V to any other vertex. And now in our case, an edge would form between 2 vertices if and only if the two vertex can be formed from each other by a adjacent circular transposition. And the maximum distance that you have would now be the upper bound, that is the upper bound on the number of transposition that is required to factor. So once you, so when you factor, it will be, suppose there is a product of 5 transposition. That means you need 5 vertices to go from one vertex to the other. You need 5 different edges to go from, and that 5 different edges would form a path, and the maximum such path would be the diameter of that graph, right? So that is what you want. So the question becomes to determine the diameter of the graph G. And you can look at some examples, say n equal to 1, 2. I already mentioned that these are trivial because there is only one element in that set. But you could go to n equal to 4, for example, and then you can see that n equal to 4 would be now a triangular graph. But I'll not do this in too much detail. Let me just mention a series of theorems that you could prove actually. So the first result that you could prove is that if n is greater than 4, then Gn is n regular. Okay. The next result that you can prove is that this needs certain other things, but you could prove that for n greater than 4, there are at least n times n minus 3 divided by 2 4 cycles. So what do I mean by cycle? By cycle, I mean a closed path. Okay, so you start from the same vertex, and then you take a path, you take a walk along the graph, and then you reach the same vertex again. So this would be, closed path would be a cycle. And if the number of edges in the path is n, then you call it an n cycle. For example, here in this graph, this closed path, so you start from v1 and you go along this direction, then this would be a closed path of 4 vertices, and this would be a 4 cycle, right? Similarly, v2, if you start from v2, you use this path and then you go back, then this would be a closed path of 3 edges, and this would be a 3 cycle. So I'm saying that for n equal to 4, there are at least this many 4 cycles in Gn. Okay. So, and the other third thing that you can prove is that for n greater than 4, at each point in Gn, or each, there are at least n minus 1. There are at least n minus 1 cycles at each vertex. Okay. So these are some results that you can prove. I had the proofs, but since there is not much time left, so I'll not do the proof really. But I really want to show you the main result of this. So the main answer to this question. Okay. So the main result is you would have a upper bound for the circular permutation, and that upper bound would be something like this. So given a circular permutation, say sigma, which is in L prime n, the maximum, since we are interested in the upper bound, so we need the maximum number of adjacent transpositions. So this will now be the circular adjacent transpositions needed to, so we want to factor the sigma, so needed to factor sigma is bounded by n minus 1 times n minus 2 divided by 4. And the proof is very nice because it uses the inversion number that we studied. But I cannot do the proof because it would need me to explain many different things, which would take maybe more than half an hour, I think now. But the proof is very nice because I like this proof because it ties up all the things that we had done until now. So it ties up the graphs that we did, and then the equivalence relation that we had, including the the strategy that we built for the first Japanese letter game, and also the inversion number that we defined long back, which we did not do anything. The definition of the inversion number was only to prove this result actually in this case. But anyway, so I'd like to end the talk with this result. So thank you so much. So if there are any questions, please, Dimpal, you can ask now.
Yes, thank you, Manjil. So, if there is any question, I have not seen any question yet. So, if you have any kind of question, you can ask. So, if you have any kind of question, can you hear me?
Well, I see some questions. So, like, well, let me because I was writing, so I did not check the question. So I see now that, well, yeah, so one of the conditions was the rank should fall below, but in the optimal solution, okay. So yeah, so this I think I already explained the solution many times, so I'll not go back again. So one question is, what is the importance of these games? Well, basically there is, so in recreational mathematics, the main objective is to have fun, really, fun with mathematics. So there is no practical application to these games. The only importance of this game is that there are some nice mathematics that comes out of it. So you could ask the same thing about many different things in life. For example, I don't know, card tricks or whatever. So there is no importance, but you do it because it is fun. And this is exactly why I'm interested in this kind of things. Well, sometimes it happens that some nice mathematics results out of studying this recreational maths, but that is not the end goal of the people who do it, really. Yeah, so it is nice, but where is it used anywhere? So it's not used per se anywhere, but for example, this result, so the main result is actually very important result, because this is much better than the previously known bound for this circular permutation. And I already explained that circular permutations are really very important. For example, if you are a molecular biologist, then you need to use circular permutations when you are thinking about this, how do we call this, splitting of genes and so on. So for example, maybe now you have heard about this, because you might have heard that that the COVID-19 virus is changing, and the way that a virus or any living being changes is by actually changing its DNA. So in case of virus, it's not DNA, it's RNA, but usually the changes happens when the DNA changes of any particular living being. And the changes in the DNA is not very easy to track. So one way of tracking the changes in the DNA is using this circular permutation. You might have seen that the structure of the DNA is a double helix. So the once you have this circular kind of structure, then the changes can be tracked using circular permutations. And so it is very important that you have a very good understanding of circular permutations. And one very nice end result of this studying this game was this result. So the main theorem that you have in your slide. So this result is actually much better than the previously known result, and this is quite a useful result. Well, I think there are no more questions here.
Link of Manjil.
Yes.
Hello.
Yes.
Yeah. Someone is asking for a link of the proofs.
Well, as I mentioned already in the first in the very first thing. So this is what I mentioned. So everything that I have said is from this paper actually. Bugs, Braid and Batches, and this is by Aloka, Dougherty and Vasquez. So if you just type this name, I think you will get the paper. It's a very short paper and it's quite interesting. So, and also there are some references in the paper that you could look at. So yeah.
I think there is no any more question. So thank you, Dr. Manjil Saikia, for this energetic session. You have actually made the whole introductory part of permutation and game theory more easier and beautiful using this ladder game. you have actually covered lots of things very easily and smoothly. Hope our participants are highly benefited from your lecture. Thank you once again for being with us. Thank you, Manjil.
Thank you so much.